That's so cool. Okay. Wow, that's amazing. It held the connection. Sweet. Okay, all the info's there. Admit. Good evening, Weston. Just so you know, the recorder's already running. So if you were going to say embarrassing stuff, don't do it.
I won't. Good evening to you too.
Hello, Richard. Good evening.
Yeah, good evening.
The recorder's already running, so be aware of that and don't say
Okay.
anything embarrassing. It's the weirdest stuff on the internet. Well, let's get the sharing started. Hopefully that'll keep it out of the way. You don't all need to see my mail. And I wanted to go here. And I'll wait a little while longer. I don't know what the internet's doing in Jawad's side of the world right now, but he's usually pretty good about logging in. So if he's not here, something's broken. Let's go see if there's any. Nope, just more work. Other. All right, well, I'll start and I'll talk slowly, and with any luck, our other two classmates will join us when they can. So I'm going to connect to Blackboard. Will attempt to do all of today in the Windows environment. I had a big presentation to TxDOT today. I've been kind of working on it for a couple weeks. You probably noticed my distraction, and it went better than I thought. And so I'm kind of relieved and ready to just go take a nap for 2 days. A feeling you all will experience in your work lives if you have not already. When big scary things go by and they're done, you feel good about it. Because I actually had to do everything in Windows today to demonstrate the product we're building for them. And also I actually had to log in remotely to a tutorial that we're building for them on Amazon Web Services. And damn it if it didn't work. The first time ever in front of a live audience, and it actually worked. So that's why I'm ready to take the night off. Okay, let's go on with our class. So you have one last thing to do for the class. I think we meet next week. I think we have 2 meetings next week. But all I have for you to do is the last assignment.
I think we only meet once next week
Even
because
better.
Wednesday is dead day.
That's a terrible name for it, but okay. So I put up project number 3. Project number 2 is not up there because you did that and I never made a formal deliverable. And there's the uploader. It's due May 10th. I think I have to submit grades on May 11th. So basically you got till a day before that. Don't worry about the points possible. I have to put a number there for the computer to allow you to have an uploader. And that's just a notation to me that whatever this is pretty important. So I'm going to read them. If I do something like a 3 points possible, I sometimes, not in your class, but in the freshman class, we've got like 70 different graded things. And so if it's only 3 points and it's there, if they get a 3, I don't even look at it. And that's kind of embarrassing, but that's just life. But a 50 will tell me to take a look at it. And in the project 3 directories, new spelling, looks like I'm trying to be French there. It should take you to this location, and there is a directory called data channel with obstruction. And in that is a topo file, and it looks like I have zipped an entire project file, although I'm not sure that the zipped file can be extracted and be useful, but the topo should be. And there's a topographic file, and there's an explanation in the problem statement. The other one is data rectangular channel. RF plane. I'm pretty sure RF plane is the topography file. There's a zipped project file, so that might extract and work. I don't think so. I don't know what file. I have a feeling file 1 and RF plane are the same thing. And then there's the actual project itself, which I'll go through shortly. And then if you actually know anything about latex, there's some other stuff here you're free to take a look at. I'm not sure it's going to be terribly useful to you for this project. So here's the problem statement. I showed you this before, but I've got the date correct, and I have the accounting number correct. So the first thing to do is to replicate the Green River example. And I would suggest not only replicating what I've done in class, but actually replicate the example on their tutorial where they cut the island out, just so you know how to do that. And the purpose of part 1 is to convince yourself you can operate the software. We had a sequence of things to do. Hopefully I can find it. Oh, rats. Where did I put it? There it is.
Dr. Cleveland?
Yeah, the protocol for building a storm model. There it is. I put this on the look down thing so it gets captured on the video.
Dr. Cleveland?
Yes,
So I tried doing the tutorial for the Green River.
yes.
I wasn't able to do the island stuff.
Okay, because
I don't know.
it doesn't have the cutout in it.
I
I'm
tried
not
to do
surprised
it.
that you can't do it because the software has changed
Yeah,
actually.
yes. Because they were saying we should use create mesh something, and I couldn't find it, so I couldn't do it.
Okay, well, we'll try to take a look at that tonight in a second.
Okay.
Let me change my video to the look down camera. So there's the sequence of building and running a storm model. Well, obviously not Green River. You need the topographic data, build the grid, boundary conditions, friction, map the attributes to the grid, then do some trial and error on simulation parameters, and then you run it, and then you interpret the output. The second problem or part is to simulate a rectangular channel. And so here's a picture looking upstream in a research flume. And so the water flow comes in through this box, spills down onto there's actual solids here, and then makes its way moving towards you in the view. Initially goes through these 3 little culverts, and then when the water gets deep enough, it'll go over the top. This is simulating a low water crossing. Here's a culvert system, and then it comes downstream of that, and then makes its way on out of the flume. And then this downstream part had various different inserts into it to cause different backups on the main model. And in these widgets down here, we're actually measuring X, Y, and Z velocity in the flow field. So the first one is a just a rectangular channel. You ignore the existence of this low water crossing. And you're given some necessary information. And your goal is to produce a simulation plot. And here's an example of one. So the channel's flowing from left to right. And using the topographic data supplied, it does a fair representation of the topography, but we're actually asking something very difficult of this particular model, which is to take a regular grid and create a triangular irregular network on it. And then the second picture down here is showing Streamlines. So when you download it, you can zoom in on these. I don't know how to zoom in because I'm doing it in Windows, which doesn't have an Acrobat viewer. And here they are at a couple of different simulations. 2,000 seconds in the research flume should be plenty of time to come up to a steady state. The research flume is only it's only 12 meters long, so that's plenty of time for everything to do its thing. And then the next part is to repeat it, except now that this obstruction is placed in the way, and to represent the three culverts because of the way the storm model works, this portion is cut out. So imagine it goes like that, drops down, comes here, comes back up, and goes over to the right. And so what you have is a wide portion of a channel, narrow portion, and wide portion. Some additional information for that, and the topographic file is called RF cut step. And then do the same kind of outputs as before and verbally discuss the difference in the two outputs. So is there an effect of the step on the velocity or not? And so here it is with the step. You should be able to detect an effect of having that step in there. And you are free to choose whether to do the advanced thing or not, because we don't have much time left this semester, but it's possible to edit the file, and you can move the cutout from the center to one side of the flume and rerun the simulation. It changes the appearance of the output, and what that does in effect is it's how I would actually simulate this for a real fluid mechanics problem. Is we're introducing an axis of symmetry right down the middle, and so we're doubling the size of our modeling regime. 4 is optional. 1 through 3 are what I'm expecting you to be able to accomplish by next week. Okay, is that fairly clear? I will take I'll take silence as a yes, and let's go ahead and be sure that we can do these parts. So I will return to Anna. By the way, welcome. And what I was going through was the third project, which is obtainable on Blackboard, and you upload it here, and it's due on May 10th. We have one meeting next week, and so what we will do for that meeting is we can use that as a workshop if you give these a try and you're having troubles, and we'll try to fix the troubles. Okay, so I'm going to do a workshop today to be sure that these data are actually usable, because I did not check that. As I told you all when I started, I was distracted with other things the last couple weeks. No, I will keep the project folders until I know. So first I want to create a new project, choose OK. And I need to download the data. So first I'm going to do rectangular channel. So rfplane.tpo, save target as, and let me create a new folder. I apologize for the rather stupid naming, but hopefully that downloaded it. Okay, import. There should be elevation. My rectangle. There's the topographic file. Okay, that looks correct. Let's go take a. There should be a way to actually look at each point. Maybe I have to build a grid. So following my algorithm here to the right, I've loaded the topo file. Next thing I want to do is I want to save my file as a project, and we'll call it my rectangle, no blockage. Take it out of context, that's actually a really funny name. Okay, so the next thing is to build a grid. Let me get a little bit more screen real estate. So I'm going to select my algorithm, polygon shape, OK. And I'll define the region. Now these red dots correspond to the upper and lower wall, or the left and right wall in the photograph. The program will work a lot better if we include them. And I am intentionally trying to neglect that first column and the last column. Because it's going to do interpolation, we need to give it something to interpolate. So there is my grid. We'll go ahead and there's no holes in it. We can add a hole. So this is what I think you do to do an island. And that creates a hole. We'll take the hole out in a second. Actually, let me see if I can delete the hole right now. Rats. I may be stuck with a hole. We'll do it again in a minute. Go ahead and create the grid. I'm not even going to mess with those just yet. Okay, that's not a very useful grid. I want to get at least 10 cells along the inflow and the outflow boundary. So I'm going to have to redraw my grid. I also want to get rid of my hole if I can. How do I get rid of a hole? Cool. I think that did what I wanted to do. Oh, I guess I'm starting over. My bad. Okay, we'll go ahead and start over anyway. So let me do it correctly. Because it's interpolating, I want to get my boundary just inside my model region. Okay, so there's my rectangular region. Now I want to create the grid. We'll go ahead and we'll take the initial defaults and see what we get. I want to count 1, 2, 3, 4. We have five entries along the edge, so we need to make our grid finer. So let's reduce our cell area by a factor of 2. Count again, 1, 2, 3, 4, 5, 6, 7, 8. So we'll reduce it again. So the reason we're looking for 10, I would love to say it's because I have intimate knowledge of that's what fluid mechanics tells us, but actually it's in the modeling primer that comes from the Storm website. They're the ones that so I'm trying to keep my cells as big as I can and get good coverage. 1, 2, 3, 4, 5, 6, 7, 8. One, 2, 3, 4, 5, 6, 7. This thing is really fighting me today. Yay, that's going to be 20. So we'll go with that grid. So there's the grid we're going to use. The next thing we want to do is boundary conditions. And to do that, we actually probably need to go back to the problem statement. So we're doing step 2 here. So the initial flow depth is 0.3 of a meter. The upstream boundary condition is 0.1 cubic meters per second. I happen to know that this should flow from left to right. But let's verify that. I don't currently have bird's eye view window. I'm trying to rotate it so I can see which way is down. I'm pretty sure it's from left to right. So we're going to make this left side our inflow boundary. So to do a boundary condition setting, we go to that and we're going to go to the add inflow. And I'm going to try to miss the corner, but I want to get the interior points. And I'm basing my drawing on the triangles right now. And we want to make it 0.1. And for what it's worth, these are actually real flow conditions taken from, I guess, 2021, 7 or 8 years ago is when we ran these experiments. So choose OK, that's our inflow. Let me zoom in a bit and make sure I haven't screwed up big time. What I'm trying to avoid is I don't want to get a second layer of triangles. It looks like I got it OK. So now we will pan over to the other end and we'll put our outflow condition, and then the outflow we're going to specify a flow depth. So we'll go to outflow, and I'm going to play the same game. Zero point. Come on, machine. Downstream outflow condition 0.3 meters. So we've got the inflow and outflow boundary conditions, and according to our thing, the next thing we want is a friction model. Zoom out a bit. So I'm going to try to get a friction model more or less coincide. Actually, I guess it doesn't matter because it can interpolate. And let me see what roughness values I want to use. 0.04. So the friction model is there, the boundary conditions are there. I'm going to go ahead and save the work. And then the next thing we do is we map the attributes. So we go back to our grid, we go attribute mapping, and we're going to put elevation and roughness onto the model. We could also put initial stage, which I haven't defined yet. We'll put the inflow and the outflow. We'll click the okie dokie, and it claims it has done it successfully. And at this point, we're ready to set up some simulation parameters. So let's go ahead and do that. We go into the calculation conditions, and we're going to set up the initial conditions from uniform conditions. We'll go back to our problem statement. So the initial x component velocity is 0.2 meters per second and y is 0.0. So we go to 0.2, 0.0. Water surface elevation is 0.3 meters. We'll leave that as is. This is actually pretty small scale modeling, so we may have to use a fairly small number here. I'm going to try microseconds. I'll do about 100 time steps. I'll plot every 10. This is just to get things up and running, make sure it's going to work. And then general conditions are fine. And at the time we did the data, the ability to do culverts weren't coded into the program yet. So I will save everything, and let's go ahead and run a simulation. Okay, that was a desirable run. 100 time steps of 1 millisecond isn't very much time. That's 100 milliseconds, which is 1 microsecond. Excuse me, 100 microseconds is 1 millisecond. Takes a little bit longer than a millisecond to get from one end to the other of this flume. So now I'll go ahead and, just for grins, we'll go look at the output real quickly. The velocity arrows are as expected, and if we were to rescale, and there was the initial velocity conditions, and for the first 100 seconds of simulation, it's trying to hit a steady state, but you'll notice that this upper portion and this lower portion have zero velocity because there's no water there. If you remember from the photograph, the sidewalls are slanted and then they drop down vertically. And so at these particular flow conditions, the water is completely contained in the pilot portion of the channel. If we go back to the picture, so our initial conditions, everything is contained between these two walls. And so these benches are not carrying very much flow yet. Let me go ahead and welcome Jawad. The recorder's been running, so you'll have no trouble catching up. I'm going through the project 3 that I've assigned and put on Blackboard and making sure that the data files are actually readable and it works. So the next thing we would do in this case would be to modify our solution parameters. Pretty sure this is a small enough problem that we can get away with what I'm about to do. That'll be Good. And I'll let it run. And it's grinding away. I may have set up conditions for failure because this number is starting to get, right now it's at 17, 20. I think it'll make it. I think we'll get to the end. When I use this tool a lot, I did a lot when we were doing these experiments, because what it does is lets you visualize computationally the effect of obstructions, things like bridge piers, culverts. You could put circular objects in it and visualize the flow field. And then we went to the laboratory and we had an underwater camera and we had other visualization techniques, including the highly sophisticated thing of putting food coloring in the flow field. And we're able to confirm that the computational visualization and what we could see in a real experiment were remarkably close. Close enough that in relatively simplistic geometries, I have faith that the STORM program produces adequate visualization of what the flow fields look like. I wouldn't trust my life on the numbers because only a fool does that, or an astronaut. But I was able to convince myself that the tool is actually what it says it is. Okay, so I've simulated, I think I've done 1.5 simulated minutes, and I know for a fact that even at a flow of 1 foot a second in that particular flume, it would only take 48 seconds to transit the flume. So I'm pretty sure that we are at a position where we would indeed have a resolved solution. So let's first just look at some interesting, pretty stuff. There's the water surface elevation. And where it has high numbers is essentially our dry cells. And where we're down here in the dark blue region, somewhere around 0.3, it's a little higher than 0.3 meters, which is about correct for those conditions. If I turn on the bed shear stress, I should get, the image should look the same as the one I just showed. And most of the bed shear is going to occur in the center line of the channel. And sure enough, it does. We have the highest shear actually near the end of the channel. So the water is squirting along here and starting to pile up at this end. And if we had the ability to resolve velocity down here, we'd see it's slightly slower on the right end than on the left end. We could turn on velocity magnitude, which is the square root of the velocity, and we should almost deduce the same. It's barely detectable in this imagery. It's faster here on the left than it is on the right. Let's go ahead and get the velocity arrows, because that was the whole point of this study. And if we choose the property, let's just shorten these arrows. So 0.1 meters per second is going to be represented by 100 pixels. And down here in the lower right-hand corner, it produces a scale. And I think I just went the wrong direction in this case. So I will change that. We will go up to 0.5 meter, 5 times 1.5. Yeah, that's about right. Okay, that's what I wanted to see. And actually, turn off the grid. So there's my velocity field at 100 simulated seconds. And we'll go ahead and we'll run the time steps through, but keep in mind what's happening. We've produced an initial condition that may or may not be an equilibrium solution. And so the time step algorithm is working through time until things stop changing. And actually that happened remarkably fast. It was doing that last time, wasn't it? Boy, I hope I saved everything. Okay, this time I'll do it correctly. I'll let it run in the background. And while that's backgrounding, I'll look at the second case. So the second case is going to take very similar information. When it's done, we'll figure out how to do the streamlines and the particle tracking. The second case is the same thing, except now this object is in the way. Nothing changes in terms of the x and y component of velocity. So one of the tricks we're about to explore is if we can just make a duplicate of the project and then change the topo file that it uses. We'll be there. We're 40% done with the simulation. And that is all that project for homework involves. So let me get this thing done. Come on, don't crash. Well, it didn't crash last time, so why would it crash this time? What could have possibly changed except for a few minutes of our lives? I say that with a necessary degree of skepticism based on past experience. I'm still confused why it crashes a lot. But considering what we paid for it, out-of-pocket cost, we paid for it plenty as taxpayers. And it is done. That is disturbing. Why is it not saving the output? Okay. I wonder if my virtual machine is running up against memory limits. Got it. So what I'm going to try to do is when it gets to the end, if it allows me, I'm going to try to save the output before it crashes. And then we can reopen it and render it at that point. If it crashes again this time, I'm going to have to give up and I'll go back to the Green River and figure out how to do the streamlines and the particle plots. Don't crash, please. 89, 90, 91. All right, now I'm trying to get over to the save thing before something breaks. Project successfully saved. Okay, there is my flow field. Let me turn off the grid temporarily. So that's what my flow field looks like. What I'm interested in is generating streamlines. And the way we do it is we turn off the velocity arrows. And so now we have generated streamlines. And they change with time step. And so all this is supposed to be a steady flow conditions. So after 40 seconds, it should get pretty stable. So there we are, about 40 seconds, and the streamlines are mostly staying put. And in the real, shiza, that's okay. At least that was saved. Try that again. You may not have that issue on your computer because you may not be hitting the memory limitations. So about 40 seconds is where I think in this particular physical conditions, things should start to get kind of stable. And so as threatened at 40 seconds, everything's kind of staying put. So that's how you can generate streamlines. You can actually increase the number of points in a streamline and get higher resolution, which in this particular example isn't very interesting. There's nothing to be gained, but if there was a lot of curvature in the system, seeing where that curvature goes is pretty interesting. The other tool that I think is really quite fascinating is a particle tracker. And in the same way we added streamlines, we can have it add particles. We'll go back to the first time step. And if you recall in your fluid mechanics class, what we're producing right there are streak lines. So at the beginning of each time step, a row of particles is introduced into the flow field. And at around 40 seconds, again, it should start to kind of look fairly constant. And I find it fascinating that this lower part here is somewhat disturbed flow, as on the upper edge, on the edges, for something that I think should be more symmetric than that. If I turn back on the grid, we can see that my drawing of the particle region wasn't as good as it could be. We don't have any information coming up here, but we can see that the main flow is going right down the center line, and we start to get mixing along the edges, which in the real model was a real thing that we could see. I'm going to go ahead and redraw the particles. And let's go like that. Apply those, choose OK. Go back to time step 1. And what the particle field should look like is a flow going down a tube. Because that's really all a rectangular channel is a tube that's square instead of circular. And from this, you can see where the high flows and the low flows are in terms of two-dimensional velocity field, exactly as one would anticipate. Most of the mass flow is going down the center, and there's not much along the edges. Oh, I keep forgetting it renews it. We'll go ahead and let it try to I'm going to let the animator go. Well, that was cool. So, so there is there's how to do that one. The next problem, and again, I hope yours doesn't crash as frequently as mine, is the same thing, but we're going to use a different topographic file. So I'm going to attempt to so that data is all still there. Damn if I know why it does that. Okay, I want to view object browser. Okay, so there's our usual setup. Okay, I'm going to attempt to save as a different project file, and this is going to be so I haven't changed anything. I've just created what I hope is a duplicate. And now what I'm going to do is on the elevation, I'm going to add, no, import stop. Need to download the file first. So with the obstruction, I'll just save it to the same place. And now we want to so points one we're going to delete. So everything else should still be there. We should still have our boundary conditions and inflow. We turn on points number 2, and you can see so you turn off the grid. There we go. There is our plan view of the object. So the dark blue, as you recall, is the lowest elevation. Light blue is a little higher, and the red were the sidewalls. And so this is representing that water crossing with a cutout in it. So think of this as a nozzle, is that the flow would come here, and it's going to have to get some fairly high velocity in this region to get through that area, plus whatever goes over the top of the step. And so now I want to, okay, grid's been created. I need to map elevation, roughness, inflow, outflow. I think that's all I need. And then let me check the calculation conditions, uniform. All right, and we will run that. With any luck, we have saved the problem of having to redraw the various polygons. Let that do its thing in the background. No point in me opening another instance, it'll just crash the. So I think the crashing is a consequence of not the actual simulation, but I'm saving too much output files, and my computer can't manage it. I find that kind of interesting since the computer has 64 gigabytes of RAM, which is 7 times more than the best laptop I have. The laptop never crashes. But these Apple products are just clunky. Three, 4, 5, 6, 7, 8, 9, done. All right, so if it crashes, no big deal. We can actually just reopen the that's weird. So I'm going to go straight to the particle tracking. We'll go ahead and put that in. We'll put in 30 points. I'm picking 30 just completely arbitrarily. We'll run them along that edge. Apply, okie dokie. So it doesn't look much different yet. Bear in mind the step is right about here. So it's accelerating through the slot. And then it's getting this S-curve shape, which I never quite, again, my intuition tells me it should be more symmetric than that. But Alariza had a good observation from, he's done similar simulations with a different CFD software. And what he's observed is that circulations actually start along the edge. And that's what causes this, this tail wagging effect that we're seeing. So if we turn on the velocity magnitude, we can immediately see the impact of putting that obstruction in a slot. It actually behaves just like a jet nozzle. We can see the same with streamlines. Let me turn off the particles so they don't get in the way. So the way I'm doing it is I'm right-clicking on the thing and I'm choosing the property editor. And then I draw where I want the streamlines to be. I choose apply and then I choose OK. And so the streamlines are yes, cat, what is it? I know it's time for you to eat again. It's been almost an hour since the last time you ate. I'll be with you in a minute. And so with the step in there, it has an impact on the streamlines. And that's all you're to do for this project assignment. So I'm convinced that the data are downloadable and this assignment is doable because I've just demonstrated the technical work involved. And what you would have to do for your exercise is to replicate this and go ahead and screen capture and produce a short write-up on what you did. And in particular, you all missed that. I have a cat in my face. I'm going to share with you. There we go. There's his ears, one ear, two ear. And he is now demanding complete attention, as cats will tend to do. The write-up is probably about like this problem statement, 4 or 5 pages, screen captures, and then address in a narrative steps you took to reflect geometry, compare the results, is the effect of the step apparent with a velocity or streamline diagram. And that would conclude your project number 3. If you're feeling frisky, you can try editing the topo file to move the cut from the center line to one side of the flume and see what effect that has. What that does is it pushes the nozzle up to one side or down to the other, whichever way you move it. And to do that, you'll have to look at the contents of those files and decipher the coordinate system. So the first is X in meters. The second is the Y value in meters. So the flume is about 2.5 meters wide. And then the side walls are set at 1.2 meters above the bottom of the flume. It looks like this is done as a flat flume. So everything is held to 0, which is not the real one. The real one has slope to it. But the whole thing at the far end is 10 meters long. So you're modeling about 30 feet by 8 feet. What do you want, Kat? That does not look comfortable to me. There you go. That looks comfortable. It should be on the keyboard now. So does that clarify the final project for the class? I will take silence.
Yes.
It's probably a yes.
Yeah.
The one project we won't get to do is, this was when we learned Storm, what we used it for. So here's a real stream, not far from here in Lubbock, 30 miles away. And we had to build a topographic model from scratch, put in some conditions, and actually do some real analysis. And what we learned is a couple of very important things. Is the way we normally do stream flows with cross sections is not terribly compatible with two-dimensional modeling, because there's these big holes in the data, and when you grid the data, you get these apparent pits. These pits, because of regularity, these are artifacts of surveying. What they're telling you is you need more information in between them, because we know this is a channel, so these blue pits should all join together, and they shouldn't look like holes. They should be channeled against the channel. And so our normal surveying techniques are inadequate. So if all you have are cross-sectional data, you can certainly build a two-dimensional model. I mean, the software doesn't care, but you need to tell your client that the lack of information between the cross sections contaminates the three-dimensional representation of the system, and our choices are to actually get real data between the cross sections. That would be the best thing. The other choice is we'll have to come up with an interpolation scheme external to the triangular irregular network scheme and populate these regions between it with, well, fake data is what it is. We have to produce artificial topography between it. And we would not have known that until we did this on this real case. So two-dimensional modeling, to do it well, has an extremely high elevation data requirement that until you've done it, you would be unlikely to notice that. We don't have enough time this semester to complete this. What I will do is I'll find the paper that was used to generate this particular problem, and I'll present that next time. So that's all I have for tonight. And I want to wish you all a good evening. And Jawad, I want to wish you a good morning and a happy day. And we will meet on Monday.
Thank you, Dr. Cleveland.
And if you're having difficulties, it's not due until May 10th. That should be plenty of time. If you have difficulties, bring them up on Monday and we'll do our best to address them. All right. Well, have a good weekend.
You too.
You
Thank
too.
you.
Thank you,
Bye-bye.
Dr. Cleveland.
Good night.
Thank you, Dr. Cleveland.
Okay. Bye-bye.
Bye.